Hello, my name is Peter Matzenbecker. Thank you for joining us today. Today we will be discussing antennas. We would specifically the power that they radiate at some arbitrary point. Let us begin with some antenna being driven by a voltage source. Whatever that function may be. However the antenna is shaped, we have some point P over here. So we have some voltage function over time, and we wish to find the power as a function of time at that point P. How can we go about doing this? Well, as with every problem, we must first define a coordinate system. This sits in three-dimensional space. We have our x, y, and z coordinate system. What exactly is going on here? The voltage source is driving charge carriers in the wire of the antenna. They will be oscillating. Accelerating charges radiate, and they will radiate out to the point P. Let us look at the contribution of one charge that radiates, and then we will build it up from there. So for an accelerating charge, what is the power that it emits? That is the first question we must answer. Conveniently, the Griffiths book has summarized the Larmor formula, which is on this website. At cv.nrao.edu. Anyhow, this is not a lecture on the Larmor formula. This is about the antenna. However, we'll give you a brief description. S is the pointing vector, which describes the power that is radiated by fields. This toroidal-looking shape is the Larmor surface. This is an equipotential surface. All points on the surface have an equal power density passing through them. As you see from the geometry of the problem below the surface, the vector is v dot. That is the direction that the charge is accelerating in, as is given by this geometry here. So we notice that the formula is 1 over 4 pi q squared v dot squared sine squared theta over c cubed r squared. And you see that as theta goes to pi over 2, it is maximized. It radiates stronger in directions perpendicular to the charge. Therefore, the power that is radiated is not spherical and radially invariant. It is of this donut shape. So, for one charge, we now know how the radiation comes off it. Four wasn't too legible. Okay. Now, what would v dot be? Well, that's the derivative of the velocity of the charge. Now, we're never going to be able to analyze every charge in the wire, but we can look at the aggregate of the charges, which would be the current density. So the current density will flow, the current will flow along the wire. The instantaneous direction of the aggregate of charge will be in the direction of the current, which would be tangent to the wire. If you're on a track, you slip off, you continue in the direction that you're going, you know, the tangent is the instantaneous rate. So we can model this curve mathematically as we do with all space curves and say that we have a curve alpha. Now, if you've seen from calculus of three variables, that's often referred to as alpha of t, the parameter t. However, this is a time-varying system, so we must reserve t for other uses. We will use n as our space curve parameter. We could say alpha prime is the derivative of all components with respect to n, and we could have alpha prime, which is our tangent. So that is going to be the direction that the charges accelerate in. You know what? Let me just move this down a little bit, this formula. It's kind of in the way of where we're going to need to be in a sec. And the norm of S would be the magnitude of the power. Okay. I'm going to say that, I'm going to say that let's go back to Wikipedia. So we're going to need to find the drift velocity. How do the charges actually accelerate as a function of voltage? Okay, Wikipedia defines the drift velocity as the average velocity attained by the charged particles, such as electrons, blah, blah, blah. We have a formula for the drift velocity here. Use the drift velocity is equal to m, where it's the molecular mass times the electrical conductivity times the voltage divided by the density, divided by the elementary charge, divided by the number of free electrons per atom, divided by the total length of the conductor. You see that it's inversely proportional to density. The more dense the medium is, the more stuff is in the way of those electrons, and the harder it is for them to move. That's why it's in the denominator. So it is m sigma delta V over rho E FL. Now, it should be noted that, let's just say this is a time-dependent system. So I'm just going to say this is U of t, delta V of t. Now, you know, in reality, time could go on and different things could change with the system. Maybe it heats up and the conductivity goes down. However, over a sufficiently short time horizon, the only significant thing that will change with time will be the voltage function. So we can rule these out as constants with respect to time. Therefore, as we said, it is the accelerating charges that radiate, not charges that are moving along at a constant velocity. So we are interested in the velocity, the derivative of velocity with respect to time. When we take that derivative with respect to time, that is encircled in blue will just be a constant. The main time varying variable is voltage. So it is as simple as differentiating both sides. No product rule will be needed. Okay, so now we have our, and just to stay consistent, it's going to be a U. We're going to replace a U with, we're going to replace V with U as to not confuse with voltage. Okay, so we have the formula for U, and we have, we just need to get theta and R. Now, it's too complicated to look at the entire curve. However, in the spirit of calculus, we will first partition our curve into many sections. Now, let us assume that this is as most wires are and is of a circular cross-sectional area. That would mean that the sections, so long as they are partitioned sufficiently small, would be like little cylinders. And you know what? Just to clean this up a little bit, I'm just going to delete this and move P down a little bit. Now, with the spirit of calculus, we are going to find the contribution from one infinitesimal length and then integrate over the whole curve. Let this point be dl of a very small length. And P will be equal to this. So the point P is just a point. However, there is a vector with components x, y, and z that will get you from the origin to that point. Now, it is just to be clear, the subscripts of x, y, and z are going to be just the x, y, and z components and not derivatives with respect to those variables, or I should say partial derivatives with respect to those variables. Now, the distance between our section that we are concerned with and our point P, we can label as R1. What would this be? Well, we already fixed alpha of the parameter n runs around the whole curve and will start at 0 somewhere and increase as you go around the curve. However, alpha of n fixed to a constant value will just be a vector in three-dimensional space. We could just say this is alpha of c with its x, y, and z components fixed. So it's a three-dimensional vector. We need to get r. Also, I should note there's going to be an alpha prime at that point. So at that, we have our section with its contribution. Its charges will accelerate in the direction of alpha prime, which is tangent to the to the segment, and they will be at some angle theta between the point P and their direction. So we need to, if we find R1, we can plug that into the denominator of our formula for the Poynting vector, and we can get its contribution. And then we will just need theta. Also, we will need to know the total charge. Well, the total charge, the charge is going to be the total charge of the segment, which would just be its charge density times its volume. So I'll just write that Q is equal to, and hold on a sec, what's the volume? Let's not forget, with sufficiently small set spacing, it is of cylindrical nature. So Q is equal to the charge per volume times the volume, which is the cross-sectional area, times the length. That's Q. So we can plug in Q. We can plug in the derivative of the velocity. Now we just need to get theta and R, and we can find the contribution of this one segment, and then we will sum around the entire curve and find the total contributions of the power. Also, it should be noted that just as the sun, well, it's 10:27 at night, but if it, in Australia, the people that are being hit by the sun are being hit by the sun from some time in the past. The sun will, the sun that hits them was sent off by the sun at some time in the past. So we must account for this. I'm in New Jersey, by the way, if you're interested. Okay, R2 is greater than R1, therefore the power through radiation that hits the point P was emanated at some point in the past. So was R1, but R2 was further in the past. If the point of P is directly on top of the radiator, then P of T is equal to some proportionality constant K times V of T. But if it's very far in the past, what will it be equal to? P of T, say that R is infinitely big. So K would have to be of negative infinite, sorry. If R is infinitely big, you would have to go infinitely far back in time to correlate the voltage with its power. That would be R over C, the speed of light, how fast it takes to get there. You know, this is in air, so the speed of light is constant. We're not in any optical materials with an index of refraction greater than 1. The units of R are meters. The units of C are meters per second. Meters divided by meters per second, that's just going to be time. Seconds, we can subtract time from seconds, and the units line up. So we're going to have to take that into account. I believe it takes 8 minutes for the light from the sun to hit you, but don't quote me. Okay, sine theta. Well, I can't tell you what theta is, but I could tell you that cosine of theta is equal to the dot product of a unit vector in the direction of R1 with the dot product of a unit vector in the direction, or the unit tangent. Now, we must dot unit vectors to not corrupt the angle. It should be noted, a cool fact from differential geometry is if the parameter is arc length, then the unit tangent will always be fixed at 1. However, that need not be done. We can just normalize easily by dividing by the length. All right, so we could say that cosine of theta is equal to this. Therefore, theta would be equal to the arc cosine of that. And we could do that. Now, what's R1? Well, I'll say that alpha plus R1 is equal to P. Therefore, R1 is equal to P minus alpha. Now, you're telling us the point P of interest, and you're also telling us the parameterization of your curve alpha, so you have all the information needed to get R1. And you have everything you need to get theta. So we have everything we now need to get the power from one point. So let us just say that, just to show you how to compute that, R1 is going to be given by, let's just, theta is equal to arc cosine of what we just mentioned, which is going to be that the subtract the vector p from the vector, subtract p minus alpha vectorially. You just subtract all the components from each other. Divide by the norm. What's the norm? By the Pythagorean theorem, the norm is the length, which is just the square root of the sum of the squares. All right, dot that with the unit tangent. As we said, just differentiate with respect to your parameter n, and that's alpha prime. Divide by its norm, which is just going to be given by this Pythagorean theorem. That's theta. Oh, what's this? This is r. This is the magnitude of r. I said r1, but it could be for any r. That's the magnitude of r, so we're concerned with the magnitude of r squared. It's easy to get that. You just take that and remove the radical. Now you also have r squared for the formula. Now we're only dealing with a little bit of length, so we're only going to get a little bit of power. The differential dl is going to only give us ds in terms of power. So our ds is going to be given by, let's just plug it all into the formula and see what we get. Q squared, so find out what the charge density of your material is, charge per volume. Q squared, V dot squared. What's that going to be? That looks like it. Yeah, that looks like it. Now, I should also say that this is a function of time. ds of t, because the voltage is a function of time. Now, that voltage is sinusoidal. It doesn't have to be, but if it was sinusoidal, it would be easy to differentiate. You're going to need to differentiate your voltage function and plug it in, and you're going to have the contribution from one element. Now, we're interested in the total, so you could say that integrate this expression over the whole parameter. However, you're plugging in this angle theta. You're going to have some complicated expression, and then you're going to have to integrate the sine squared of that complicated expression. Now, I mean, maybe you could use a half angle identity and say that sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta, but that's probably going to be hard to do or not have a closed form solution. If you can find one, more power to you, but a more reliable way to get answers is going to be with some sort of numerical method. We're just going to replace the integral with some sort of finite sum. I mean, that's all an integral really is. The s, it's an elongated s for the summation. Now, say that we've broken it down. This is parameter 1, n equals 1, 2, 3, 4, 5. N equals all those all the way around. So we're going to let n, our index for the count, run from 1 to lowercase n runs from 1 to uppercase n. Uppercase n is the total number of sections that you choose. Choose enough that it's sufficiently small. Such that, choose enough that the sections are cylindrical in nature. As we said when we were talking about the sun, that's going to be T minus R. But remember that R runs over our sum, so that those R's are going to be dependent on where you're at. Some are further than others, so that's going to be R of n. divided by the speed at which the light reaches. See? You know what? Hold on a sec. I said dl. Just as the integral was replaced with the sum, the dl will be replaced with the length of the section. Well, that length of the section is going to be the total length of your wire, uppercase L, divided by the number of sections. Squared sine squared theta, which also is dependent on the index. Cool. So go around. That is the formula. How exactly can we use this? So let's do an example. Well, yes, let's do an example. We're going to use a parabolic antenna. Now, you know, with a parabola, y is equal to x squared. So let's just say that this is x, this is y, this is z. That's our parabolic antenna at some point P. Let this be equal to whatever, I don't know. Let's negative 2, 4, 8, wherever that is. We're going to drive, the voltage is going to be V of T is going to be equal to sine of T, the simplest voltage I can think of. What is the power of T? Let us begin with saying that, well, first we need to parameterize the curve. So let n equal x, y equals n squared. This lies at z equals 0, so there is no z component. So alpha of n is equal to x, n, n squared, 0 with 0 z component. Okay, you would say that that's the parameter. Now, to program this, you could say n equals lin space. Let's say that this runs from -2 to 2. So our parameter n runs from -2 to 2. So lin space of -2 to 2, let's say that it has 100 points breaking it up. We have 100 evenly spaced points for our parameter n. So plugging in the first one, say the first one is at -2, alpha of 1, index 1 would be -2, 4, 0. Now you just have a number what did we say? We said that R is equal to P minus alpha. So R is an index too. So R of 1 is equal to P minus alpha, negative 2, comma 4, comma 8, minus 2, comma 4, comma 0, negative 2 minus negative 2, so negative 2 plus 2, 0, comma 4, minus 4, 0. And then so forward. Now you can get your theta of 1 the same way. You plug in the numerical values into this expression for theta, you know, right here. And then you have it. So I'm not going to do that right now, but theta of 1 equals something else as a number. Question for you to answer. Plug that in. You get theta of 1. Now, run it over the entire array of your value index of n. So you'll see here we have theta of n equals 1 all the way down to theta of n equals upper capital N. The same goes for R. You have your thetas and your R's. You plug those in. And then you sum over all the points. Now we have theta of t, say theta of t equals 1. We would do all this. Oh, also, if v of t equals sine of t, then v dot of t is going to be equal to cosine of t. So plug that in up top. For a given point in time, you can run the summation over all points and get a given power. Given point in time, run the summation. Okay, so the voltage is fixed, whatever that is. At a given point in time, well, I mean, it varies, but at a given point in time, you fix your point in time, run the summation all the way from n equals 1 to n, and you get some power, whatever that is. And then you do that same process for different values of t. And then you get something else. Now you have data points. You could do some sort of curve fit on that, maybe with the pseudo-inverse or a similar method, and you can get an approximation for the power as a function of time from the voltage as a function of time. So if you want to see more general trends, run this same point for a different, run all this process for 1 point P, and then move P somewhere else and look at where else the power is radiated. So if you have any ways that we can improve this, feel free to contact me. If not, thank you for watching. I dedicate this video to my former professor, Jefferson Cartano, who passed away at the young age of 47 in September. He is missed by all of his students. I also dedicate this video to the many great YouTubers who came before me, including, but specifically 3 blue, 1 brown. Thank you and have a nice night.